Hello everyone, my name is Michael Horn, and today we are going to be looking at a problem in which you have three gravity-trained tanks, each at different elevations, as you can see here on the diagram. We are going to draw out our process first so we understand where all the variables sit and what each of those variables mean. And then we are going to derive a dynamical material balance, along with using a proportional only controller to manipulate the flow into the first tank. And then once we work through that, we're going to do some simulations and things of that sort that we will get into once we get to that point. Alright, so let's begin. So as you can see, as I mentioned before, we have our three tanks at varying heights, and we are going to give all of the variables labels so we understand what we're looking at. We will start with three flows. We will label this one Qn. Flowing from tank 1 to tank 2 will be Q1. And tank 2 to tank 3 will be Q2. Now, there's also a small outlet at the bottom of each tank where the flow is flowing from one tank to the next. And we will label these as AH. In the problem statement, we are listed that AH is equal to 0.1 meters squared. Along with that, there is a cross-sectional area at the top of each of these systems. We'll label that as A, and A is listed at 1 meter squared. Now finally, the last part is the liquid. In each of these tanks, all at different heights, we will label this H1, H2, and H3. So, this is our depiction of the process that we will be working through, and next we will be deriving the dynamical material balance. Okay, so I realized I forgot to draw this final outlet stream here, Q out. Now, we're going to set up our equation. So, we start with our density, our area, and our height as given in the problem, but as we said earlier, the height will be changing with respect to time. So, we're going to add d here and dt. This will be set equal to the density Qn minus the density at Q out. Now, one assumption we can make is that since we are dealing with the same substance throughout the entire process, these densities we are able to cancel out. We're able to isolate Qn, but we are not exactly sure what Q out is, so we're going to have to use Bernoulli's equation to figure out what that is. So after this cancellation, we have dAh over dt equals Qn minus Q out. But like I said, to understand what Q out is, we're going to have to use Bernoulli's equation, which the first aspect of this is the injection, which is P2 minus P1, the pressures over density, plus we are going to do the potential energy, which is G times H2 minus H1, plus the kinetic energy, which is going to be the change in speeds squared V2 minus, velocities, not speeds, V2 minus V1 divided by 2. This is going to be equal to the friction factor. Now, there are also some assumptions we are able to make in this equation. So since the entire system is exposed to the same atmospheric pressure that is not changing, we can assume that these two variables are going to equal 0. So 0 divided by anything is going to be 0, so this cancels out. And then also, we're able to assume that our velocity into the system, V1, is also going to be 0, so this can be canceled out. And then friction is not going to play any effect into this system here, so we're going to also cross this out. Okay, so the next step in the process is subbing this Bernoulli's equation into the equation right above it. So we are going to isolate V squared in this equation, which we're going to get equals as V equals 2G H2 minus H1 all inside of the square root, which can then simplify down to V equals 2GH. Okay, now when we want to sub this V into this equation up here, we then get negative dAh over dt equals These, I noticed I'd made these capital Q's up here. They're meant to be lowercase q's, so I'm going to adjust that now. So this will be Qn minus, it will be AH times this V that we just subbed in, which is going to be 2 radical 2GH to the 1/2. Now the final step that we want to do to get this fundamental derivation is we're going to want to bring this A right there over to the other side, which will leave us with negative dH dt is equal to 1 over A that we just brought over from the other side times Qn minus AH 2G radical H1/2. Now, this, what we just derived, my backpack just fell. That was that noise. What we just derived here, we're going to be able to manipulate and plug into the system above at various heights to, better understand our system. So now we are going to actually apply this equation that we just derived to each one of the tanks. So we are going to have a system of 3 different equations that will each be applied to each of the tanks above. It's rather intuitive. This is probably one of the easiest parts of this process. So the first tank that we labeled, with our variable 1, we are going to have negative dH1 over dt equals 1 over A Qn minus AH times 2GH to the 1/2. But this H is going to align with this H1 that we have here. We're going to also have an H1 right there. So we're just tailoring these two H heights above to the actual first drain tank that we applied. So this is going to be the first equation. I'm going to get rid of these red circles. And now for the second tank, if you can guess it, we are going to do H2. So same equation. I'll make this a little bit easier actually. We're going to highlight all this, duplicate, and we will swap out the H1 for our H2. We also need brackets there. And then finally, our third tank, as you can guess, is going to be H3. Now, these 3 equations that we just derived are going to allow us to go into Google Colab and actually simulate this process, tailor some more things that are given in the problem statement to make things a little more specific. So essentially we derived these equations right here to allow us to simulate this process in any type of coding format that you would prefer. And that's what we're going to go do now. I actually just realized there's a slight mistake in the work shown above. I realized it as I was checking over before we moved into Google Colab. I'm not sure why, but I accidentally added a negative sign here in the front of these 4 equations. There is no negative sign, and I wanted to correct that error before we moved on. All right, I adjusted the camera angles so we are able to better understand what I'll be coding in Colab. And as you can see in part A here on the left side of your screen, we're going to be using Colab to simulate this process that we just derived the equation for with 3 tanks. And then we're actually going to go into finding the maximum value of the controller gain, which is kind of be the barrier between a stable system and an unstable system. Okay, so I had to take a quick break. My iPad was dying. I had to plug it in. So next, we are going to, as I said before, import all of the functions or libraries that the actual Google Colab and code is going to need to perform the calculations that we have derived in these equations. So the first one that we're going to do is import numpy as np. This will do most of your arithmetic that the code will need help with. And then we're going to do from Skippy dot integrate import solve IVP, and next will be from plotly dot subplots import make underscore subplots. Okay, so now we have pretty much the actual framework behind the code that we're going to build ready to go. And now we are actually able to start defining our variables. So we are first going to need our define the first set of variable. You can name it whatever you like. I'm just going to name it beta. Beta is going to be equal to this. I'll highlight it so we can see. In green right here is going to be equal to that highlighted section right there. So we're going to do A times H times square root. What is the function for that? Dot square root, I believe. Okay, so sorry. This is going to be AH times NP, which is, as you can see above from NumPy, is going to be square root of the 2G. And we are not going to include the H yet because the H is going to be changing over time, so we cannot actually set that as a variable. So now we will define the right-hand side of the equation. So def right-hand side, and we have to define t, so time obviously, and then in the equation above, as you can see, we did not define h yet, but we cannot use h, like I mentioned, it's going to be changing over the time, so we'll do vector. So now we are going to move into defining some of the variables. Like I said before, we'll have h1, h2, and h3. And these are going to be equal to that VEC above. And then we also have Q1, Q2, and Q3. Now these are going to be equal to that beta we have above, but we are going to multiply that by NP square root of H1. And then we will do this. We're going to do that for H1, H2, and H3. So we will copy this, paste it. This will change to H2. This will be H3. Now we have set up our code in more of a step-by-step format, so we're able to move on to the next step. So now we will start to step into the proportional controller. This is actually going to run on a error value. The error value we will set as E. We're going to set that equal to the height starting point minus the final height, which we would have as H3. And then next we are going to actually define Q in, and we are going to set that to the original Q height, which we will say Q naught. We're going to add the controller gain, which we will do KC, and then finally we will multiply that by the E that we just set above. And then obviously we want all of this to be able to, return us a value, so we're going to do return. And then we will do the first value. It kind of goes back to the derivation that you can see on the right side of the screen with the three equations. We're going to have three different three different equations inside this return value. So first we are going to have our Q in minus Q1 divided by the area. And then we will also have, moving down the line, we will go to Q1 minus Q2, divide that by the area. And then finally, no comma there, you guessed it, Q2 minus Q3 divided by the area. So now that we have all of these set, we can go in and actually start assigning some of the variables with the numeric values that were given in the problem statement, and we can start to work from there. So let's define this. So, oops, did not mean to do that. So first we have our area, and in the problem statement, it is listed as 1 meter squared. Now, we'll also remember have the smaller area that it's actually flowing out of into the next tank that we listed as AH. That is going to be 0.1 meters. Meters squared. Next, we have gravity, which is going to be 9.8 meters per second squared. And then our initial flow rate, which we listed as Q in naught. And in the problem statement, that was said to be 1 meter cubed per second. So the next variable we want is H naught. And we are actually going to have to go back to the iPad for this to be able to solve. We're actually going to go look at this equation here. We're going to circle all of this. And actually the first thing you're going to want to do is copy. So the first thing we're going to want to do, oh shoot, I'll just rewrite it all. So it's dH over dt equals 1 over A Qn minus AH 2G H to the half. Now, the first thing, like I said, you're going to want to do is define if it's linear or, oh, you couldn't even see me writing, I'm sorry. There we go, this is what I just wrote. You're going to be able to want to see if it's linear or nonlinear. And when the first thing that is a telltale sign is this 1/2 right there, that is going to let you know that it is non-linear. Now from that, we're actually going to go and isolate H naught. And once you do that, you're going to get H is equal to H naught is equal to Q in naught over AH. And this is all going to be divided by 2G. And now we can type this in to Colab. So let's plug this in to Q and naught H, and then that. That would be divided by 2G. We also mentioned how there is a height starting point, HSP, and in the problem statement, it was listed that it was 20% higher. So what you would do here is just do 1.2 times the variable above, H naught. Okay, so we are going to add three more variables right now. The first one we are going to add will be the KC value, which, like we said before, is just controller gain. We're going to set the equal to 1 and then just make a note so we know that this is the controller gain. Next, we are going to make the tendencies, which is just essentially how many points we want to collect from this. We'll do 1,000 for easy math. And then we will do t-plot, which is going to make these values actually plot and be able to understand them on a graph. And so what you're going to want to do there is do NP. This is just pulling from the library in space. And then you're going to do the number you want it to start at. And then in the middle, it'll be your tendency value and then what number you want it to go to. So to make it simple, we would want to go from 0 to 1,000. So our line spacing would line up exactly with every value that we are collecting from the tendencies above. So 0, comma, tend, comma, 1,000. So as you can see, we will now be actually plugging in a solving equation for this. We have all of our variables, we have all of our libraries imported. We just actually need to actually solve this. And I added HSP right here because we want an actual output for all this work that we've been doing. So our solving equation, we're going to start with res equals solve.ivp. And then in this solve.ivp, we're going to have to put things of our method, which will be Radul, and just things of that sort. So we'll start with right-hand side, obviously, because that's what we'll be solving. And we will do 0 to 10, which is how many numbers we want. And we will do a NP pulling from that NumPy full. And here we will put 3 because we're solving for 3 things along with H naught. Do another comma here. And then this is our method like we said, which we will do Radul. Dense underscore output equals true. Okay, so that is the solving equation. So we also still have to add in our actual plotting mechanisms. So the first is going to be hplot. This is going to allow us to plot the values that we are getting, and we're going to set that equal to res.sol tplot. Okay, and then we actually have to set what that variable hplot is equal to, and that's going to, just like we've had 3 equations this whole time, we're going to keep continuing that pattern. So we're going to have h1 plot, h2 plot, and h3 plot is all going to be equal to hplot. So now we have the plotting section complete, and now we're going to actually work on displaying these plots, because right now it would be doing the work, but it wouldn't actually be outputting a graph or plot for us to see. So that's what we're going to get into next. Okay, so before I started plotting, I went through some of the code just to make sure everything was running correctly, and I wanted to update. I did move some of the variables that were here up here because I was getting an output saying they were not defined before the equation. Along with I missed a colon here, and then I made some syntax errors in the resolution here. So I'm sure I'll probably run into more errors, but right now I think we're good to continue. So the first thing we're going to do is actually start making the subplots, which is going to be fig equals minus make dot subplots. Enter. And then next we are going to add the 3 separate lines being graphed for 3 different equations. So we have fig dot add underscore scatter, and then we are going to have x equals t plot, y equals h1 plot, and then we will have mode equals lines and name equals h1. Now we are going to do this. Something is red, something is telling me that's probably not right. So let me pause real quick. Okay, I got that cleared up. I'm not sure what was going on, but something wasn't working, retyped it out, and we're good. So now we have our h1. We're going to, that is incorrect. So we are going to now add fig. You can see it's already suggesting that it goes to y equals h2 plot, name h2. That's exactly what we're going to want. So we can, there we go, tab over. And then we're going to want h3 plot also. So thank you, Gemini, for that. Tab. So now we have our scatters. Each one of those lines that you see will be representing a line that we're going to see on our graph. All right, so I went through one more final check. Wanted to share some of the more issues that I had. Actually, I kept getting an output saying h2 plot was not defined. I found out I made a typing error up here, right there. I had h2l plot. I'm sure you probably noticed that when I was typing it in and were yelling at me to change it. But I got that fixed. And then also here at the bottom, I inputted fig.update underscore layout. It allows you to adjust the graph that you're going to output. So here, since my collaboratory background's black, I'm going to make mine black, just easier on the eyes, and then also made the height and width 600 and 400 respectively. So now this is going to output a graph, and what we're going to be looking for is oscillations, just similar to like a cosine or sine graph. If it looks different from that, that's going to alert you that this is an unstable process, and we're going to need to change that Kc value that we originally set to 1. So when you originally set your Kc value, if it's too high, it's not going to oscillate. So right now we have it set to, I believe, 1. Yeah, 1 right here. And let's see what happens. Okay, so obviously this does not look like a sine graph, so we're going to lower this down a bit. You're going to want to make these steps rather small because a super tiny difference in Kc value can make a big gap. So it's not like you would want to just drop it down to like 0.2 or something like that. So let's try 0.85. Let's see. And we're going to run all. Obviously still not what we want. So we're at 0.85. Let's go to 0.75. Let's see that. No. Let's go down to 0.7. Something might be wrong here in my calculations. I'm going to double check and then be right back. All right, we're back. I realized when I made the error with HL pot, I redefined it and then I fixed it. But so I double defined it and it was creating a bunch of weird issues. So, okay, let's restart. Kc's 1 right now, and you can see we get this value. So like I said, let's drop it down very slightly to 0.85. Let's try. Let's see what we get. Still not, ideal. Let's drop it down to 0.7275. See, now this is obviously much better, but you can tell it's a little bit shifted to the right. You can see that it's getting larger and larger and larger, which means we have a little bit too big of a number. So let's go down very slightly. Let's try 0.7. The opposite. So let's split the difference. We'll go to 0.725 and we'll run this. And that is about as good as we're going to get here. You can see all 3 lines are oscillating, which just means this is going to be as stable as our system can be. So I would like to say thank you for watching this video, and I hope you're able to learn something today. Had a weird glitch with the sound there, but thank you for watching my video. I hope this was easy to follow along and understand. And yeah, that's all I got. Thank you.